Background. Modern automatic speech recognition systems often use a large number of spectral/temporal features, i.e., 50 to 100 terms, computed with typical frame spaces on the order of 10 ms, partially because of these high dimensionality feature spaces. Large vocabulary continuous speech automatic speech recognition often have several million parameters that must be determined from training data. Zhao et al., 1999. In this scenario, the curse of dimensionality, Donahoe, 2000, becomes a serious practical issue. For high recognition accuracy with test data, the feature dimensionality should be reduced, ideally preserving discriminability between phonetically different sounds, and/or large databases should be used for training. Both approaches are used. Despite growing computer size and computer storage densities, it should be noted that in principle the amount of data needed for adequate training grows exponentially with the number of features. For example, increasing dimensionality from 40 to 50, increases the need for more data by a factor proportional to k 50 to 40, equals k10, where k is some number representing the average number of data samples distributed along each dimension, and almost certainly 2 or larger. Thus, for good training of model parameters, increasing dimensionality from 40 to 50, considered a modest increase, could easily increase the need for more data by a factor of 1000 or more. Therefore it seems unlikely that increased database size alone is a good approach to improved ASR accuracies by training with more and more features. In this lecture, some techniques are presented for reducing feature dimensionality while preserving category, i.e., phonetic for the case of speech, discriminability. Since the techniques presented for reducing dimensionality are statistically based, these methods also are subject to curse of dimensionality issues. However, since this dimensionality reduction can be done at the very front end of a speech recognition system, with fewer model parameters tuned than in an overall recognition system, the curse can be less of a problem. We first review some traditional linear methods for dimensionality reduction before proceeding to the nonlinear transformation, the main subject of this lecture. Principal Components Analysis, PCA, also known as the Carhoonen-Loewe transform, KLT, has been known of and in use for nearly a century. Fodor, 2002, Duda et al., 2001, as a linear method for dimensionality reduction. Operationally, PCA can be described as follows. Let x equals t be an n-dimensional, column, feature vector, and y equals t be an n-dimensional, column, feature vector, obtained as the linear transform of x, using the beam transformation matrix A, i.e. y equals ATX. Let x caret equals by be an approximation to x. Note that x, y and x can all be viewed as, column, vector-valued random variables. The goal of PCA is to determine A and B, such that EX minus x2, is minimized. That is, x should approximate x as well as possible, in a mean square error sense. As has been shown in several references, for example, Duda et al., 2001, this seemingly intractable problem has a very straightforward solution, provided x is zero mean and multivariate Gaussian. The rows of transformation that have been shown to be the eigenvectors of the covariance matrix of x, corresponding to the largest eigenvalues of this matrix. The columns of B are also the same eigenvectors. Thus the forward and reverse transformations are transposes of each other. The components of y are uncorrelated. Furthermore, the expected value of this normalized mean square error between original and re-estimated x vectors can be shown to equal the ratio of the sum of unused ANA values to the sum of all eigenvalues. The columns of A are called the principal components basis vectors and the components of y are called the principal components. If the underlying assumption of zero mean multivariate Gaussian random variables is satisfied, then this method of feature reduction generally performs very well. The principal components are also statistically independent for the Gaussian case. The principal components account for or explain the maximum amount of variance of the original data. Shows an example of scatter plot of 2D multivariate data and the resulting orientation of the first primary principal component's basis vector. As expected, this basis vector, represented by a straight line, is oriented along the axis with maximum data variation. Scatter plot of 2D multivariate Gaussian data and first principal component's basis vector. Line is a good fit to data. Depicts data which is primarily aligned with a U-shaped curve in a 2D space, and the resulting straight line, PCA, basis vector fit to this data. Since the original data is not multivariate Gaussian, the PCA basis vector is no longer a good way to approximate the data. In fact, since the data primarily follows a curved path in the 2D space, no linear transform method, resulting in a straight line subspace, will be a good way to approximate the data with one dimension. Scatter plot of 2D multivariate Gaussian data in first principle components basis vector. No straight line can be a good fit to this data. Linear transforms for the purpose of reducing dimensionality while preserving discriminability between predefined categories have also long been known about and used, Wang and Paliwal, 2003, and are usually referred to as Linear Discriminant Analysis, LDA. The mathematical usage of this is identical to that for PCA. That is y equals ATX, where x, y are again column vectors as for PCA. The big difference is in how A is computed. For LDA, it has been shown that the columns of A correspond to the largest eigenvalues of SW-1 SB, where SW is the within-class covariance matrix and SB is the between-class covariance matrix. Often SB is computed as the covariance of the category means. Alternatively, it is sometimes computed as the grand covariance matrix over all data, ignoring category labels, identical to the covariance matrix used to compute PCA basis vectors. SW, the within-class covariance matrix, is generally computed by first determining the covariance matrix for each category of data, and then averaging over all categories. The explicit assumption for LDA is that the within-class covariance of each category is the same, which is rarely true in practice. Nevertheless, for many practical classification problems, features reduced by LDA often are as effective or even advantageous to original higher dimensional features. Depicts 2D2 class data, and shows the first PCA basis vector as well as the first LDA basis vector. Clearly, for this example, the two basis vectors are quite different, and clearly the projection of data onto the first LDA basis vector would be more effective for separating the two categories than data projected onto the first PCA basis vector. 2D2 class data, along with first LDA basis vector and first PCA basis vector. The classes would be well separated by a projection onto the first LDA basis vector, but poorly separated by a projection onto the first PCA basis vector. Another linear transformation technique, related to linear discriminant analysis, but which accounts for the, very common, case where within-class covariance matrices are not the same for all classes, is called Heteroscedastic Discriminant Analysis, HDA, Saon et al., 2000. The process for HDA is described in some detail by Saon et al., and illustrated in terms of its ability to better separate, as compared to LDA, data in reduced dimensionality subspaces, when the covariance properties of the individual classes are different. HDA suffers from two drawbacks. There is no known closed-form solution for minimizing the objective function required to solve for the transformation, rather a complex numerically based gradient search is required. More fundamentally, with actual speech data, HDA alone was found to perform far worse than LDA. Nevertheless, if an additional transform, called the maximum likelihood linear transform, MLLT, Gopinath, 1998, was used after HDA, then overall performance was found to be the best among the methods tested by Saon et al. However, ASR accuracies obtained with a combination of LDA and MLLT were nearly as good as those obtained with HDA and MLLT. A detailed summary of HDA and MLLT are beyond the scope of this lecture. However, these methods, either by themselves, or in conjunction with the nonlinear methods described in this lecture, warrant further investigation.